Hi. In this video, we're going to talk about pressure methods and reaction rates. We have spoken about concentration dependent terms and we have spoken about temperature terms and their effect on reaction rates. But when we are dealing with gases, I'm writing this down so that we never forget about this. When we are dealing with gases, especially, we have to deal with pressure measures. Okay, and generally the systems are described by partial pressure or total pressure. Okay, so generally, we have seen that when we want to describe the reaction rate. Uh, Let me just reiterate this part for sake of easier understanding. We what do we do? We write the rate of reaction. Let's say I'm considering A gives some products to us. Okay, so the rate of reaction becomes minus RA equals to minus 1 by V dNA by dt. Okay, now this you will write as a product of rate constant with the concentration dependent terms. Now this concentration dependent term in case of reaction rates where gaseous measures are involved becomes a function of pressure. Okay, so this can be in the form of like partial pressure or in the form of for gases K F of pi, pi being the total pressure. So generally we total pressure as pi and partial pressure is usually denoted as small p. Okay, I'm writing I over here depending on your component. So this is the general expression that comes out for gaseous systems. So when you are converting, or rather, I should say, when you are developing the rate equations to study the kinetics, what we do is directly the pressure term is used. Okay, so directly whatever expression you have been supplied, you use that. Let me explain this to you with the help of an example. I think that will help us grasp these things better. So let's say we have a batch reactor and we have a specific component A which is decomposing. Okay, so A is just decomposing and within a batch reactor. And this entire phenomena is given using pressure units but at two different temperatures. So let's say at 400 Kelvin the rate of reaction is 2.3 Pa square. So this is the partial pressure expression. And at 500 Kelvin, the rate of reaction is again 2.3 Pa square. Okay, so qualitatively, of course, you can say that the rate of reaction are same, but there is a motivation why I took this particular example. Now, another thing to note, since we are engineers, we have to be careful about units. So, minus RA, it has the unit mole per meter cube seconds, and partial pressure has the unit of atmosphere. Okay, now our target is to evaluate the activation energy term. Activation energy means E. So generally, in these cases, what we do is we use the rate constant expression and use Arrhenius type of relation. So if we want to tally through the Arrhenius type relation, our formulation is like ln of k2 by k1 equals to E by R 1 by T1 minus 1 by T2. Okay, so let us go through the calculations with the pressure units itself. So ln of K2 by K1 in this case becomes ln of 2.3 by 2.3, which is ln of 1 and that becomes 0. Okay, so if your left hand side becomes 0, then obviously you can say that E is equivalent to 0. But this is not correct. Okay, reason being, whenever you are dealing with pressure units, your first target is to convert that pressure into concentration term. So please remember, let me write this in a different ink so that we never forget about this. Transform PA into CA, then find activation energy. That is the correct way to do things. Okay, the activation energy, if calculated using the pressure units, is incorrect. Okay, so you have to use the concentration dependent term. And intuitively, if you realize, you see the discrepancy in the units of rate of reaction and the the term which was dependent on pressure. So here you already have the consideration of the concentration term. So obviously it is the right thing to do is to convert the pressure measure into a concentration measure, and for that you will use the ideal gas law. So simply what we'll do is we'll use ideal gas law. Let me also write this down. Ideal gas law will be used. Okay, so now let us just write the rate equation first with all the units. So minus RA equals to 2.3 into PA square, right? This was our rate equation at either of those temperature. So at 400 Kelvin and at 500 Kelvin. Now the unit of RA is mole per meter cube second, and the unit of PA square is atmosphere square. So the unit of this K factor, or 2.3, is mole per meter cube second with atmosphere square in the denominator. So then you see this is dimensionally balanced. Okay, I'm sure you are aware of dimensional analysis. If not, if you need more clarification on that, then definitely comment on this video so that I can bring up some content on that as well. So if we now apply the ideal gas law. Ideal gas law is Pa equals to Na by V RT, which can be written as CART. Okay, so this is ideal gas law. If you combine this, then you will get minus RA equals to 2.3 Ca square into R square into T square. So now you see the temperature dependence, the concentration dependence is all incorporated into the main rate equation. Okay, so now if you do the mathematical uh, study at 400 Kelvin, you will be writing minus RA equals to 2.3 multiplied by Ca square into the appropriate value of R, because here we have more meter cube atmosphere by mole Kelvin. So accordingly you will choose the value, that is 82.06 into 10 to the power minus 6 multiplied by 400 square. Okay, so this reduces to 0.0025 Ca square, where K1 now becomes 0.0025 mole, sorry, this will be meter cube on top, meter cube per mole second. Okay, similarly at 500 Kelvin, The rate equation gives the form 0.0039 Ca square. So from here K2 is now 0.0039 meter cube per mole seconds. Now you apply the Arrhenius type equation. So now it becomes ln of 0.0039 by 0.0025 equals to E by R 1 by T1 minus 1 by T2. So if you solve this, you will get E is equals to 7394 joules per mole. So now you can see that you are getting difference in the values of E when you are using P or C. But like in this case you got E equals to 0, so you can be like you can say okay, something is going wrong here. But sometimes you cannot detect that mistake. So it is easier to like remember always that whenever you have pressure measures involved, convert it to appropriate concentration measure and then proceed with the rate equation finding. Okay, that is it. Thank you.